It's one of the most ambitious geological mapping projects in modern times. A country well known for its oil, its sand dunes, and its mushrooming development, wanted to get a more complete picture of what it's made of and how it came to be.
The Ministry of Energy and Infrastructure of the United Arab Emirates asked the British Geological Survey to find out.
Information was gathered from about 30,000 locations. Over 8,000 rock samples collected. Geologists will have their survival skills tested by searing heat, blinding sandstorms,
we must get out of the water and get onto higher ground,
and deadly flash floods over a 10-year period. Can the BGS fill in missing chapters of an epic geological story? Will they find hidden mineral treasures within the UAE's ancient landscape? Builders, planners and prospectors all rely on geological maps. This is the story of how the Geological Survey was conducted and how the geological history of the country and its landscape evolved. This morning in an Abu Dhabi villa, the British Geological Survey team is deciding what to map and who will do the mapping.
John is doing this area here, and that area just there is your bit, my bit. Everything north of that pipeline has been completed. We need still to get permission to go into this security area around this oil field, so that's still outstanding.
Richard Ellison is the team leader. He's been with the BGS for over 30 years.
That's the one that we did together, you remember?
Yeah.
Bob Thomas has been on this decade-long mapping project since it began in 2002.
Yeah. This is an area that's been a bit tricky in the past.
Yeah.
I've got a few gaps to fill in around here.
Helen is the newest member of the team. It's her first international assignment.
It's fine white sand and it's really easy to get stuck in there.
Each red dot on the map is a survey data entry. When the process is complete, the team will have made a total of about 30,000 entries.
See what I mean about the dunes on dunes? You've got the massive dune forming a big ridge and you've got all these smaller ones riding up on the edge.
These are among the biggest dunes in the world, and they still hold secrets about their origins, which the geologists are determined to reveal.
It's going to get a bit bumpy, I'm afraid. This is the Liwa Desert where we are now, which is where the biggest dunes in the country are. In the flat areas in between them, you can get sabkha areas forming and you get salt pans crystallising out that's covered in gypsum, a flat-lying area where the water table is actually not very far below the surface.
Collecting samples and mapping the sabkhas, or salt flats, provides insight into climate change and clues about changing sea levels over the past 10,000 years.
There had never been a full-scale national survey of the geology of the United Arab Emirates. Where are you going to put your ports? Where are you going to build your new towns? Is this the right place to put a nuclear reactor? Are you going to have potential problems with earthquakes? All these factors, you learn the answers, or some of the answers to those, from studying geology.
In some parts of the country, especially along the coast, the sabkhas have also been integral to a geological process that has shaped the destiny of the UAE.
Sabkhas are really important environments geologically. They occur at various times in the geological column. And one of the aspects of sabkhas that we're looking at is the development of algal mats. Do you see these orange layers here? This is an algal layer. Actually, if you were to trace them, you could trace them right out to where they're actually at the surface, where they're black and they look completely different. And that's where the tide comes in on a regular basis, and that's where you start to get the algae, okay? So it might seem insignificant here, but when there's a situation where there's numerous algal layers deposited, this is a source for oil. When the rocks are buried and the oil is generated, it's the algal layers which are one of the sources of oil. If we can identify this kind of environment in rock cores, which are drilled for oil exploration, then we can make the analogy and we can start to predict where oil might have formed and therefore where it might have migrated to form reservoirs. Most people would say that the mega fields, the giant fields, are probably all being discovered, but you never know.
What we're doing here is we've got a series of very fine grey sandstones here, which is forming the top of this little plain area that we have, and we have to try and see what's underneath. At the top of this little excavation, we've got this grey sandstone. Here it is outcropping up here, and the base of it is falling around here. This stuff is that sandstone, and below it you can see the bedding planes in this sandstone outlined by grey and orange layers. This is the Aeolian sandstone. Aeolian means derived by the wind. So all these dunes that we see around us, they're all Aeolian deposits, whereas this sandstone is what we call a fluvial deposit. It was deposited by water action.
The fluvial deposits may be evidence of an ancient river system.
This is the point that we are now in this position amongst all these sand dunes. So that is where I made my observation point, and then as I make the point, I get this screen, which is where all the various information is added onto the computer. There's a screen here where I write Arada formation, which is the main, which is the formation that we're looking at.
In addition to GPS and satellite imagery, the laptop holds a diary of all geological observations.
And we have this screen here, which is comments, which is where I add the general description of the locality that we're engaged in.
What I'm doing here, I'm just digging a shallow section through this sabkha. This fantastic wrinkled dark surface is a living algal mat. Absolutely fantastic. And so if I put my fingers under it like this, we can get the whole mat to come away. It's like a piece of leather. It's fantastic. And it's only 2 or 3 millimeters thick here. And you can see that underneath the algal mat is this soft, mushy mass, and it's just a mass of gypsum crystals, tiny gypsum crystals. This is very, very characteristic of an active sabkha in the intertidal zone, which is really where we are. If the sea continues to rise slowly, successive layers of algal mats will be deposited in this fashion, and with geological time passing, those will be more deeply buried, and they ultimately will release oil.
Getting stuck in the dunes with your 4x4 is an occupational hazard of mapping a vast desert. Bob has ventured deep into the so-called empty quarter, on the lookout for fossilized dune formations. They may help solve one of the biggest riddles of the UAE desert. Where did the mountains of sand, which originally created the mega dunes, originally come from? And when exactly did they arrive? This is a single grain of quartz sand from the UAE, as seen under an electron microscope. And there are a few more like it where this one came from. Was erosion from an exposed Gulf seabed the source of the desert sands? Or did ancient rivers deliver the sediment which formed the dunes? It'll take the geologists over 4 years to begin to answer this mystery. While 80% of the UAE is covered in sand, there is a spectacular mountain range in the northeast of the country called the Hajar Mountains. These mountains have long fascinated geologists. They contain some of the world's best examples of the forces which build and erode mountains. The team will spend many months mapping the rock formations in the Hajar Mountains.
I think probably that one, yeah.
Yeah, down there. See where that bus is now?
For mapping the mountains, the team is joined by Catherine Goodenough.
Which is this one coming down here, because this is going to take us down here and bring us into there.
We're here.
What are you trying to figure out right now?
We're trying
Where we're going.
The logistics of beginning a survey of the mountains are simple. From Abu Dhabi, take the main motorway for about 4 hours northeast. Take the dirt roads until you get to the rock-strewn valleys. Ride along the valley floor as far as you can. Then hike for a day or two to get to the most remote mountain tops and outcrops.
Probably up here at about 1,100 metres above sea level, and as you can see we have this lovely fossiliferous limestone with these white fossils. They're gastropods, or snails really, sea snails we call them.
One of the things we'll look for is fossils, well-preserved fossils in the rock. Then there are other forms of dating that we can do in the lab.
What was once a sea floor teeming with life has been uplifted 2,000 metres by tectonic forces. Bob and Catherine are atop layers of limestone which are 5 kilometres thick. These layers were deposited in a warm, shallow sea over a period of 170 million years during the Permian to Cretaceous period, which is more than 65 million years ago. The fossils in this sample, one of the 8,000 collected, will be studied to investigate its age.
Often the limestones don't have big shells and things like we can see easily, so you have to look for the microscopic fauna inside them. And you look at the microscope and can recognise all these different types of tiny sea creatures which may be a millimetre or less in size. And the types of creatures and the mixtures of the groups together can tell them often quite accurately how old those rocks are.
This is the Hajar Mountains in all their glory. We're looking at a pile of sedimentary rocks. The rocks here have been folded and thrusted, and that's a result of compressive tectonics.
These mountain peaks were likely the very first bits of land to emerge from an ancient sea to form what is today the UAE. Field mapping and sample analysis is constructing a chronology for the formation of the Hajar Mountains.
What I'm looking for is a layer that is weathered easily. That's what I'm looking for. So these beds of limestone are quite massive, and between the massive beds of limestone there are some indented areas which are beds that weather out more easily, and that's where the fossils ought to be found. So if I come down here...
Richard is on the lookout for the fossilised remains of nummulites. They were the largest single-cell creatures of their day.
We'll try and now look for these nummulites in situ, in position in the rock, and in fact here they are. And can you see they're arranged so that they're flat lying essentially, which is an indicator that there were probably very few, so these things just floated down gently to the sea floor. And wherever we find this type of rock, this is muds with these nummulites in it, we know, of course, that we're in the same rock unit, and that we've found this all the way along this mountain front area.
These countless layers of limestone are hardened sea floor sediments with skeletal remains of sea organisms. Limestone deposits were formed in a sea on the eastern margin of the continental shelf of the Afro-Arabian continent. This is where the shallow sea ended as it fell off towards the deep ocean floor. It was the very edge of the Afro-Arabian continent. Limestone layers that flowed down the edge of the continental shelf overlie darker rocks, which are an ancient reef which grew about 100 million years ago.
The reef was formed right on the margin of the continent.
Fossils of this ancient coral reef are about 30 kilometers from the current coastline.
Maybe 96 million years ago, there was this enormous, catastrophic mountain building event.
By the compass, this 4x4 is heading southwest. Geologically, it's driving off the edge of the continental shelf and heading to the bottom of the deep and ancient Tethys Ocean. Eventually, it will drive through every layer of the ancient oceanic crust beneath the Tethys Ocean until it arrives at the Earth's mantle.
We're going southwest, parallel to the Dipper Zone. The mountains on the right are part of the Dipper Zone itself.
The Dipper Zone is a transitional zone of rocks between the edge of the continental shelf and the deep ocean floor. Thanks to tectonic movements which have pushed the sediments of the Tethys ocean floor on top of the continental shelf, there's nowhere else on Earth quite like it.
We have very much a mixture of rocks, a mixture of those which we can attribute to the continent and a mixture of those which we can attribute to the deep ocean. If we look at this rock in detail, we'll see that it's composed, it looks almost like a fruit cake in that it has a matrix with large lumps of different size and colour within it. And this is what we call a tectonic mélange. That you will see over there, for example, there's a large maroon mass. That's a deep oceanic chert that we find within the melange. If we look down there, we see a dark grey rock. That's a volcanic rock. It's a basalt, which was probably taken up also from the ocean floor. And if we look a little bit over there, we see a brownish rock. That's a bit of a deep water limestone. So again, it's showing we have this complete mixture of rocks. That's why we use the term mélange.
The Dipper Zone below contains a diverse range of deep sea sediments, as well as remnants of seafloor volcanoes.
On a global scale, this is probably the best place in the world to study the transition from a continental margin through to the deep ocean. These rocks here in the Dipper Zone were pushed up onto the continental platform at about 96 million years ago, followed behind by the ocean floor itself. And this all happened very quickly at about 96 million years ago, and by 95, 94 million years ago, we already had a mountain range here which had risen from the ocean to a height of at least 3 kilometers above sea level.
Where the UAE, with its deserts and mountains now sit, was once upon a time a shallow sea. Where the shallow sea ended and the deep ocean began was at the edge of the Afro-Arabian continental shelf. 96 million years ago, things started to change. As a result of volcanic activity far out in the ocean, new crust or ophiolite was forming. The ocean floor expanded outwards. The knock-on effect was intense pressure where the sea floor butted up against the continental shelf. An unstoppable force was pushing against an immovable object. The oceanic crust and continental shelf began to fracture. Limestone sediment, which had accumulated over millions of years at the bottom of the sea, began to buckle and fold. The seabed was being pushed skywards. The ocean floor, with its diverse layers, was also being pushed upwards. and taking some of the Earth's mantle along for the ride. The sea floor broke in two. A section pushed downwards by the incoming crust triggered volcanic activity as it melted from the extreme heat of the Earth's core. The ocean floor that ended up on top of the continental shelf is now known as the UAE ophiolite.
To see such a section of at least between 13 and 15 kilometres of vertical crust, to see it exposed, all laid out before us in sequence over the Hajar Mountains, has been an absolutely fantastic experience.
The maroon-coloured rock below was once the uppermost sedimentary layer of the ocean bottom. It's called chert.
I'm going to take a sample of this because we want to do a micropaleontological analysis of the rock. It has these organisms called radiolaria in it, which can help us date the rock. I'm also going to measure its magnetic susceptibility with this capometer. And again, we tend to do this on a regional scale, and it helps us with our interpretation of the aeromagnetic map of the country.
Complementing work on the ground, the Ministry of Energy and Infrastructure commissioned an extensive series of aerial surveys, which covered over 80,000 square kilometers.
Aeromagnetic surveys reveal the presence of magnetic elements in the ground below. Gravity surveys reveal rock densities. And radiometric surveys offer a window into natural radiation levels below the Earth's surface. A series of deep seismic surveys were also conducted across the UAE. Earth-pounding trucks analysed over 250 kilometres of terrain. A section of a seismic survey vehicle lowers itself to the ground and begins to pound. Return signals from shock waves translate into pictures of underground formations. All these surveys reveal structures deep in the Earth's crust and provide insights into the geological evolution of the country. They may also provide clues for new sources of oil and gas. After the geological fruitcake of rocks, which is the transitional Dibber zone, the thick ocean floor was next in queue to be shoved up onto land. Where Catherine and Bob are now strolling was once 12 kilometres beneath the seabed.
It's really odd to be able to actually sit on this material that came from so far beneath the seabed.
Sections of the thick sea floor, whose fate is to be pushed up onto land, are the ophiolite.
Ah, that's a good bit.
Ophiolite is made up of parts of the oceanic crust and the mantle that lies underneath it. It's part of the seafloor, essentially. It can be several kilometres thick. This one's up to almost 10 kilometres thick.
Some geologists get very excited about ophiolite. Ophiolite offers a unique window into the elemental forces that create ocean floors, move continents, make mountains, and shape the planet. After a thin slice of rock is cut, it gets ground down to a micro-thin wafer, thin enough to allow light to pass through its structure.
When we look at the thin sections, we can tell a whole range of features about where they formed in the ophiolite. Simple things like the grain size tells us what depth they formed at. As you go deeper down into the crust and even into the mantle, the crystals gets larger and we can see crystals with our naked eyes. We can also use the ratio of those minerals to recognise different varieties that have formed at slightly different times. There's actually about 500 kilometres long of this big chunk of ocean crust which has been thrust up. Another thing about this area is a lot of these rocks are very fresh. They've been very, very little altered. They've not been disrupted as much by faulting as they are in many places, so we can see by far the best preserved sequence of ocean crust that's been thrust up in the Oman and the UAE together. This is the best example in the world.
The team will spend 4 years surveying, dissecting and dating the ophiolite. Catherine is intimately familiar with all its layers.
At the top, you've got pillow lavas, which were erupted onto the ocean floor.
Pillow lavas got their name because of their shape. They're the result of lava flows up from deep underwater vents that are rapidly cooled as they hit the cold seawater. These pillow lavas are on a mountain over 100 million years old, but it's a process that still takes place on the ocean floor.
Underneath that, you've got the sheeted dike complex, which is essentially the feeders for those magmas coming to the surface.
The darker slice of stone here was once an active sheeted dike. In its day, over 100 million years ago, it was a busy fountain of hot lava up from the Earth's core.
Beneath that, we've got gabbros, formed in a magma chamber, hundreds of meters down beneath the surface.
The gabbros are rocks formed from cooling lava deep underground. They can sometimes contain valuable mineral resources. This mountain of gabbros was the lowest portion of the oceanic crust. At the top of this mountain is a remnant of a transitional zone between the ocean crust and the mantle called the moho. All these layers are collectively referred to as ophiolite. The fingerprints of tectonic activity are everywhere.
The ophiolite, it's pushed itself up over here and it's transformed these rocks into these highly buckled and folded strata, and this folding is actually due to the massive forces from the ophiolite mass which is coming from down there up over my head here.
This is where the ophiolite has been thrust over the rocks of the continental margin by the huge forces of plate tectonics.
In addition to holding secrets of an epic story, ophiolite may also contain hidden treasure.
Well, what we've got here is this sort of brownish mass, if you like, which is actually a vein of something called dunite, a slightly different rock type. And within the dunite, we've got these little black specks, and these are chromites, we call them. But the exciting thing about these is that sometimes within these little crystals, you find platinum.
Another precious element for village life to survive in these mountains is water, and it doesn't rain very often. Mountain villagers have been digging wells to access aquifers for thousands of years. We were about to take a closer look at the bedrock being excavated, when a sudden rainstorm intervened. Heavy rain is rare, but when it happens, the wadis or valleys between the mountains are dangerous places to be. A warning came over the walkie-talkie.
The water is beginning to cascade down over the rock, and there's a definite possibility of a flash flood, so we must get out of the wadi and get onto higher ground.
The hazards quickly became apparent. Puddles moving along the gravelly dirt roads were gathering pace and merging. The ground couldn't absorb the water fast enough. Within a matter of minutes, a trickle became a torrent.
This is a flash flood in action. This is how mountains erode away. This is an enormous rainfall event which has produced a lot of cascading material, cascading water down the mountains. If this were repeated, say for example it rained as heavy as it's just rained for 2 minutes, say it rained for a day of that intensity, you can imagine the amount of water that would be in this wadi, maybe 4 meters of water. Then you can start to imagine how much material will be washed down by that rainfall.
No sooner did these mountains emerge from the sea, did rainfall begin to chisel away. And in the past few million years, there have been lengthy periods of heavy rain. Erosion would have been much greater in the past than today. Sediment being washed off the mountains began to fill in the remains of a shallow sea. Ancient river systems were formed. The rivers delivered rocks, pebbles and sediment to the western part of the country. The groundwork for what would become the United Arab Emirates was being laid.
6 to 8 million years ago, we know that there was at least one very large river, perhaps 100 or more meters wide, flowing out of the mountains towards what is now the Arabian Gulf, with a lot of fossil fauna, elephants, giraffes, hippopotamus, crocodile, and so on. The climate was clearly different then because there was enormous rivers flowing through the country. The shifting of the world's climates can be seen visibly here in the Emirates.
200 kilometers west of the Hajar Mountains, on an island called Shwayhat, just off the coast of the UAE, there's evidence of the ancient rivers in rocks just a few million years old.
This outcrop immediately above shows very clearly the boundary between red sediments and grey sediments, and that's particularly significant for us. The red sediments are deposited in an arid environment, and the grey sediments are part of the deposits from a major river system.
Do the ancient rivers help to answer the riddle of the sand dunes? Were they the major source of sand and sediment which formed the UAE desert? More testing and dating was necessary. The team surveyed numerous UAE islands. Karnain is a small island about 80 kilometers off the mainland. It contained one of UAE's biggest geological surprises. Welcome to the remains of an ancient volcano.
We can see here that the lava, this is actually lava, it's a very, very treacly. So you can imagine all these little flow folds that you can see, they're all due to the viscous flow of the material as it's coming out of the vent. These black features here, these are volcanic bombs. So in other words, these have been blown out from very explosive activity. They've been fired far into the air and they've come plop in the lava, which is itself flowing down the flanks of the volcano.
The most perplexing aspect of this island is that volcanic rocks on the surface were dated to be 560 million years old. Rocks of that age are usually found a dozen or more kilometers underground.
Yeah, this was totally unexpected to us. It's come up from a depth of about 13 kilometers.
There's something tectonic happened about which there is absolutely no prior evidence in this region.
That's right.
The team concluded that the geological force which pushed this lump of ancient volcano to the surface was a thick, rising layer of underground salt. This is a seismic profile of the trail left by a rising layer of salt. The salt layers are particularly important in the UAE. In addition to uplifting the odd volcano, their underground movements can cause rocks to buckle into pockets, which become reservoirs for oil. Bob is on the lookout for fossilized dune formations to take a sample for dating. The fossilized dunes were cemented in place as a result of moisture or rainfall at a time when the climate was less arid.
I'll try this place here. It looks a little bit softer.
Geologists have ways of making these grains of sand reveal their secrets. In addition to taking samples for dating, Catherine is using a technique called strike and dip. She is measuring the inclination of laminations in a sand dune about 12 million years old.
We're looking at the steep sides of the sand dunes, and we can use the dip of these surfaces to understand where the winds were coming from.
This is definitely better. It's going in easy, and it gets harder and harder as you get
To
further
accurately
into the
date a sample of quartz sand,
material.
it's essential to extract the sand without exposing it to sunlight. The sample will then be prepared for a test called optically stimulated luminescence, or OSL dating.
Okay, the OSL technique, what it's actually dating is the last time that the grains of sand in this rock were exposed to daylight. When it's very firm like that, we can be absolutely sure that the material in the middle of the pipe has never been exposed to sunlight, since it last lay on the surface of the desert, which is what we actually want to date. I have here the business section of the Gulf Times. But we just need to really put a wad in at this end, because it's critical now that we don't allow too much of the sand to fall out of the far end. Okay, it's very full, so I'm going to have to just put a bit out, but it's fine because they only use a few grains from the middle of the pipe. So this is now fairly good.
Combining a technique for dating the sands with insight into the direction of the ancient winds, the geologists are halfway towards solving the desert riddle. "4,000 miles away at Aberystwyth University in Wales, Bob's dating sample is being opened in dark room conditions. The grains of sand are carefully selected, bathed in acid, and take weeks to prepare.
The signal that we're looking at is actually very light sensitive. Once we have those quartz grains, then we can do the luminescence analysis and measure the luminescence signal trapped within those quartz grains. We typically look at something the order of between 50 and 200 grains at a time. Many minerals, and quartz in particular, is able to store energy within it. And it gets that energy from natural radioactivity in the environment that surrounds us all the time.
The quartz begins to absorb radiation as soon as it's buried and out of sunlight. The controlled exposure to a laser beam will release and measure the accumulated energy.
Our role is trying to give that context of when did these deposits get formed, and therefore narrowing down the options of where the potential sources of them are.
One more piece of detective work is expected to narrow the possibilities even further. OSL dating tells when the sand arrived. A technique called zircon dating will reveal the age of the source rocks. The source rocks were broken down by weather and erosion into sand grains.
This sand is mainly quartz sand, but within the sand there's minute amounts of a mineral called zircon. So we can actually get the zircons out of the sand in a laboratory, and we can date them, and we can see the age of the rocks which actually formed the sand in the first place. We might see rocks which are derived from the very early history of the Earth. We would expect to see a spectrum of ages. We would expect the entire history to be recorded in this one bag of sand.
And the age range of the source rocks? Between 50 million and 3 billion years old. The mapping process will also produce a timeline for the arrival of the dunes, as well as the formation of the mountains. The Hajar Mountains do have some well-known mineral resources, which the UAE has long put to use. This is one of the biggest limestone quarries in the world. Limestone is a key ingredient for making cement.
The Ministry of Energy and Infrastructure Survey has identified new sources of high-quality limestone.
Every year, up to 50 million tons of it are extracted to feed one of the biggest construction booms this country has seen in its history. Zircon testing quickly established that Hajar Mountain erosion and its ancient rivers were not the source of the desert sands. The sands are mostly quartz, but there is very little quartz in the Hajar Mountains. Another long-held assumption was that the sands were erosion off an exposed Gulf seabed during the last ice age, when sea levels were much lower. But there's very little quartz in rocks exposed on the Gulf seabed. The origin of the desert sands was the mountains, but not the Hajar Mountains.
By doing zircon dating on some of the sands, some of the Aeolian sands, we've managed to work out that most of the material was derived actually from the Arabian plate itself, from Yemen and the highlands of Yemen and Saudi Arabia.
It was ancient rivers from the mountains of Yemen and Saudi Arabia which first carried the quartz-rich sediments to the Gulf. It was then blown back off an exposed Gulf seabed by the ancient Shamal winds to form the dunes.
Much of this sand came from those highlands of Saudi Arabia and the Yemen, and over time it was reworked by winds to produce these sand dunes we see here today.
After surveying tens of thousands of sites, the Ministry of Energy and Infrastructure project will produce a series of 45 geological maps.
This is a map of actually the coast, the Arabian Gulf along here exposed in the coast, and then heading further inland this way. And this is the generalised vertical section that you get on every geological map. It's a bit like
the maps will identify countless colour-coded rock types, and the accompanying reports will provide a summary of more than 400 million years of geological history in the UAE. For planners, prospectors or builders over the next 100 years, these geological maps will likely be their first stop. And whatever you decide to build, the higher you go, the more you need to know what's below, especially if it's one of the tallest buildings in the world.
We knew we had a very tall, heavy building to put on the ground. We had to make sure that the capacity of the ground was sufficient with the foundation to take the loading imposed. Geological maps is the first thing you'd look for just to get an overall idea of what to expect below the ground.
It's the fundamental first step for any major infrastructure project anywhere in the world, really. First step is to look at the geological mapping to understand what it's telling you.
We've looked at the geology of the UAE as a whole, brought it all together and really understood the geological history of the country for the first time.